All right, well, welcome everybody to our weekly Wednesday webinar series. Thanks to today's first session sponsor, GeoComfort Systems have earth-powered HVAC to help you and your clients get to net zero energy target easily and affordably. Several projects we have worked with these systems have achieved the Zero Energy Capable or ILFI Zero Energy certification using low energy but comfortable HVAC systems provided by GeoComfort. Besides forced air, GeoComfort systems have an all-new water-to-water system that can power your water heater, radiant, driveway melt, pool, hot tub, and more, all without additional water heating. Bonus, 30% tax deduction is reapproved by Congress and is retroactive for 2017 projects. Make sure you get your system spec'd by the end of this year, 2019, to get that full tax credit, but then tax credits still remain throughout that. Thanks to our session main top tier sponsor, T-Stud. T-Stud is the 2019 Green Builder Media Sustainability Award winner for structural ingenuity. So what is a T-Stud? This T-Stud is a game-changing technology. It solves the #1 nemesis of construction industry, how to cost-effectively stop the transfer of outdoor climatic heat or cold from affecting the interior of a structure's ambient room temperature. Plainer terms, a T-Stud is the best piece of lumber available to minimize the outdoor temperature from coming through all the framing members in a wall to negatively affect your client's heating and cooling bills. It's a thermally broken insulated wall stud assembly for use in exterior walls and party walls. It's an engineered building product that uses 2 lumber members and an internal truss system and a froth-in-place closed cell foam that has a global warming potential of less than 1 and is EPA compliant for 2020. The T-Stud provides a 99% complete thermal break through the wall assembly with just 1 product. The T-Stud raises the bar on 6 major construction concerns: thermal breaks, structural strength, wind loads, sound transmission, fire safety, mold, termites. It's not complicated. It's quite easy to replace the traditional 2x lumber with T-Stud with little no additional training. Plus, it can be used as studs, jack studs, king studs, sills, cripples, headers, top and bottom plates, and rebates may be available within your state or local utility.
All right. Great. So let's move on to kind of the idea of the perfect wall. It really is simple. You bring the structural elements of the building inside and you put the primary control layers that we just discussed to the outdoors. Again, it goes by a lot of different names. The perfect wall has been kind of credited to Joe Stiebrick, and he certainly popularized it. He gives credit to the Canadians for kind of coming up with this concept in the 60s. Many other groups have picked it up and run with it with names like Persist and Remote, Perform, Outsolation. We call it ETMS, Exterior Thermal Moisture Management System. It really doesn't matter. It's the idea of bringing the structure inward and pushing the controllers to the outdoors or the outside of the structure. And so again, in its simplest form, on a wall and structure, some type of control layer for air, water, and vapor, indicated in black, if you will, and some type of thermal insulating layer in the bluish color. Then with a cladding that is vented and dried. It just doesn't get any simpler than that. And this wall simply works everywhere, all climate zones. It's just a very robust approach. Now, there are challenges, of course. We have to attach the cladding to the structure, so that requires some connections and some detail. But again, at this conceptual level, this is incredibly simple and simply works everywhere. And the same thing can work for a slab or a roof, and I won't go through those in great detail. I've got some slides here, but again, just accentuating this idea that this concept will work for roofs, work for a slab, and again, structure of the inside, air, water, vapor control, thermal insulation, and then basically in this case, drainage and drying with a drainage layer under the system and then the earth. Well, it's all well and good in the field, in the plane, if you will, of the wall, roof, and slab, but we have to connect things. That's why we use the pen test. But again, the idea of how do we carry the continuity of these control layers through our construction details is critical, of course. And I'll show you some details on that when we get into our example systems. So put the structure on the inside, and in a way, I use this story of the 3 little pigs. I use whatever you want to hold the roof up. It could be light frame, steel, wood. It could be timber frame, concrete masonry. You could use a thin SIP. I'm going to introduce a system that we're using called the solid panel system that has no studs at all. The point here is now just focus on structure. Getting yourself a structure that's obviously rigorous, robust, meets codes, is resilient to wind and storm events, etc. And then we'll move on and put the thermal, moisture, and air control layers on the outside. So it is important to now think about those control layers. What are they? That's important, but as equally important is how and when do they get put on. The whole idea of the sequencing, the construction process is critical. I'll just show you again some conceptual details. Joe, again, I borrowed this from Building Science Corporation, shows this as the institutional wall with a masonry structure, the exterior control layers, and a brick veneer. And this is a timeless wall that will last forever. You'll note at the bottom of the illustration, the vapor drying direction is illustrated here. The inside can dry to the inside, the outside elements will dry to the outside behind the, in the vented cavity behind the cladding. A commercial wall, steel stud. Don't bother insulating the inside of the steel stud. That doesn't work very well because of the conductivity of the steel. Again, you'll put your sheathing, you'll put your control layers, you'll put your insulation and vented cladding. And again, it could be brick, it could be some other type of material. Again, with a vapor drying potential in both directions from the air-water vapor control layer. Here's a residential wall, and just for illustration purposes, brick was used here again. Clearly, it's not the most common cladding, but put clapboards on the outside on a furring strip. Everything still applies. In this case, it is a hybrid insulated wall. It's using wood framing, and so you can insulate the cavity to some extent. We'll talk a little bit about the rules for that here in just a second. Some people say, oh my goodness, it's so complicated. Well, yes, it is, but you know, it can be also simplified. Here's a masonry wall sprayed with closed cell two-part foam. Foam can be a vapor retarder, foam can be an air barrier, foam can be a water control layer if it's done properly, and obviously foam's a good thermal insulation. So one layer, all done. Again, with a vented, drain, drying cavity over it. I just want to briefly introduce this concept of the hybrid wall and essentially why folks want to move to exterior or should move to exterior insulation. Essentially what you're doing is trying to warm up the first condensing plane, which in this case we'll call our sheathing of our frame wall system. And by adding sufficient thermal insulation to the outside, that warms up the sheathing temperature. Once the sheathing temperature gets warm, essentially above the indoor dew point, then the necessity for an interior vapor retarder on the cavity or an interior air barrier to prevent that air from reaching the condensing surface goes away. And so what that does now is it starts to free up the thought about what happens on the inside and outlets and all those interesting problems go away, and we can now put our air, vapor, and water control in the middle of the wall, but we have to add enough exterior insulation to keep that location warm. It's very simple. I'm not going to go through this because I'm short on time here, but I simply will add that you know, you can look at this later and you'll just see that this warms up the sheathing and brings it out of potential for condensation, whether it be due to diffusion or even air transported moisture across the cavity. It also allows you to use less expensive cavity insulation to get a portion of your insulation value. And again, you'll see that play out in our final walls, or at least one of them, two of them. So here's the ratio of exterior to interior from John Straub. It's an excellent book. Again, it's in my resource list, High Performance Enclosures. And it just says, based on your outdoor temperatures that you're trying to design for, and based on the indoor humidity that you're trying to design for, what ratio or what fraction insulation needs to be on the outside. You know, and if it's incredibly cold out and you're trying to carry incredibly high humidity, you need a very high, let's see the bottom right corner, 86% of the insulation has to be on the outside. But if you're in normal conditions, and by the way, for the outdoor temperature, you can use the average temperature for the coldest month. You know, in our climate zone, we're talking about a reasonable indoor humidity of 35% and outdoor temperature 14 degrees. We're talking about basically 50% external to interior insulation, half and half.